Time travel is real, not in the movies, not in science fiction, not in some theoretical future when technology catches up. Right now, today, this very second, there are objects moving through time at a different rate to you, objects that have aged less than they should have, objects that have experienced less time than identical objects sitting still. We have measured it, repeatedly, precisely, beyond any scientific doubt. The GPS satellites orbiting above Australia right now, the ones your phone uses to navigate, are running on clocks that tick at a different rate to the clocks on the ground. If engineers did not correct for this time difference, every time you used Google Maps, your location would drift by about 10 kilometers every single day. The correction they apply is a correction for time travel, not metaphorical time travel, not approximate time travel, actual, measured, Einstein predicted, experimentally confirmed time travel. Today, we are going to understand exactly why this happens, how fast you need to go to travel meaningfully through time, and whether traveling backward through time, the kind you see in films, is something physics allows. Crikey, let us go. G'day and welcome back to Curious Physics AU, the channel where we take the most extraordinary ideas in science and show you the genuine physics underneath them. I am Abdullah, and today we are tackling time travel. Properly, honestly, without the hand waving, because here is the thing. Time travel forward in time is not a speculation. It is a confirmed experimental result, a consequence of Einstein's special and general theories of relativity, both of which have been tested to extraordinary precision. What is speculative is time travel backward. And we will be honest about exactly where physics stands on that question too. Three things we are covering today: time dilation from special relativity, moving clocks run slow; gravitational time dilation from general relativity, clocks in weaker gravity run fast; and the question of backward time travel, what physics actually says. No flux capacitors, no wormholes today, just the real, confirmed, beautiful physics of time. Let us go. Before we talk about traveling through time, we need to establish what time actually is at the physics level. And here, as usual, the honest answer is more interesting than the textbook one. Newton thought of time as absolute, a universal clock ticking at the same rate for everyone everywhere in the universe. 1 second for you, 1 second for me, 1 second for a spaceship traveling at half the speed of light. That picture is deeply intuitive. It matches everyday experience. It is also completely wrong. Einstein, in 1905, proposed something radical in his special theory of relativity. Time is not absolute. Time is relative. The rate at which time passes, for any given observer, depends on how fast that observer is moving and how strong the gravitational field they are in. Two identical clocks, perfectly synchronized, will tick at different rates if one moves faster than the other, or if one is deeper in a gravitational field than the other. This is not a property of clocks, it is a property of time itself. Einstein showed us that space and time are not separate things. They are woven together into a single four-dimensional fabric, space-time. And just as the geometry of space can be curved, so can the geometry of time. Moving through space affects your movement through time. Mass and energy, curving space-time, also curve the flow of time. Your watch is not measuring time. Your watch is time. And that time is personal, relative, different for every observer in the universe. That is the foundation. Now let us see what it means for time travel. Special relativity makes a precise mathematical prediction about time and speed. The faster you move through space, the slower you move through time. This is time dilation, not a metaphor, a precise, calculable, measurable effect. The equation that describes it involves what physicists call the Lorentz factor, gamma. As your speed approaches the speed of light, gamma increases, and time dilation becomes extreme. Let us make this concrete with numbers, because Feynman always wanted concrete numbers. At 10% of the speed of light, about 30,000 kilometers per second, time dilation is about 0.5%, barely noticeable. At 90% of the speed of light, time runs at about 44% of the normal rate. For every year experienced by someone traveling at that speed, about 2.3 years pass for someone stationary. At 99% of the speed of light, time runs at about 14% of normal. For every year of travel, about 7 years pass for someone stationary. At 99.9% of the speed of light, Time runs at about 4.5% of normal. For every year of travel, about 22 years pass outside. Here is the classic thought experiment with an Australian twist. Two identical twins are born in Sydney. Call them Mia and Jack. At age 20, Mia boards a spacecraft and travels to a nearby star at 99% of the speed of light. The round trip takes, and from Jack's perspective on Earth, about 10 years. Jack is now 30. He has aged a decade. But Mia, due to time dilation at 99% the speed of light, has only experienced about 1.4 years of travel time. She returns to Sydney aged 21.4. Jack is 30. Mia is 21.4. They were born on the same day. Mia has travelled forward in time, relative to Jack, by more than 8 years. Not by magic, not by wormhole, by moving very fast through space. This is not science fiction. The physics is identical to what governs GPS satellites and particle accelerators. The twin paradox, experimentally confirmed with atomic clocks on aeroplanes in the 1971 Haffler-Keating experiment. Mia's journey is physically possible. Building the spacecraft is the hard part. The time travel itself is already written into the laws of physics. Special relativity tells us speed slows time. General relativity adds another layer. Gravity also slows time. The stronger the gravitational field you are in, the slower time passes for you relative to someone in a weaker field. This is gravitational time dilation, and it is just as real and just as measurable as velocity-based time dilation. Here's the intuitive picture. In our previous video on gravity, we discussed how mass curves space-time. A deeper gravitational well means more curved space-time, and more curved space-time means slower passage of time. Standing at sea level in Sydney, you are deeper in Earth's gravitational well than someone standing at the peak of Mount Kosciuszko, Australia's highest peak at 2,228 metres above sea level. The person on Mount Kosciuszko ages very slightly faster than you. Their clock ticks very slightly faster, by about 15 microseconds per year faster. And now, the GPS proof, the one that makes time travel undeniable. GPS satellites orbit at about 2,200 kilometers above Earth's surface. At that altitude, the gravitational field is significantly weaker than on the ground. Weaker gravity clocks tick faster, by about 45 microseconds per day faster than ground clocks. But the satellites are also moving at about 14,000 kilometers per hour. That velocity causes special relativistic time dilation, slowing their clocks by about 7 microseconds per day. Net effect, GPS satellite clocks run fast by about 38 microseconds per day compared to ground clocks. That sounds tiny. But GPS works by measuring the precise timing of signals from multiple satellites to calculate your position. A 38 microsecond error per day, uncorrected, accumulates to about 10 kilometers of positional error per day. Every GPS device in Australia, every time you navigate to a servo on a road trip, is working because engineers applied Einstein's relativistic time corrections. Every navigation system on every Australian road is a daily demonstration of time travel physics. Einstein predicted this in 1915. Engineers confirmed it when GPS was built decades later. The confirmation was not a surprise. The physics was right. Time dilation from both gravity and velocity is not theory. It is engineering reality. Let us talk about the experiments, because Feynman always said the test of all knowledge is experiment. Experiment 1, the Haffler-Keating experiment, 1971. Physicists Joseph Haffel and Richard Keating flew cesium atomic clocks around the world on commercial aeroplanes, eastward and westward. They compared these clocks to identical clocks left at the US Naval Observatory in Washington. After the flights, the flying clocks showed different times to the stationary ones. The differences matched Einstein's predictions, accounting for both velocity time dilation and gravitational time dilation, to within experimental error. Flying clocks, different times, exactly as Einstein predicted. Experiment 2, muon decay. Muons are subatomic particles created when cosmic rays, high-energy particles from space, slam into Earth's upper atmosphere at about 15 kilometers altitude. Muons decay radioactively with a half-life of about 2.2 microseconds. At the speed they travel, about 98% of the speed of light. Classical physics says they should decay before reaching Earth's surface. They should not survive the 15-kilometer journey. But they do. We detect them at sea level all the time. Why? Time dilation. From the muon's perspective, traveling at 98% of the speed of light, only a fraction of a microsecond passes during the journey. They have not had time to decay yet. From our perspective, their internal clock is running slow. Their decay is time dilated. They live long enough to reach the surface. Cosmic ray muons are raining through you right now, through the roof, through your body. About 1 per square centimeter per minute. Each one a tiny time traveler, surviving longer than it should because of special relativity. Confirmed, measured, real. Experiment 3. Optical lattice clocks. Modern atomic clocks are so precise they can measure time dilation between clocks separated by just 30 centimeters of height. The clock 30 centimeters higher ticks faster due to the slightly weaker gravitational field. 30 centimeters, measurable time dilation. The physics is not subtle, it is precise. It is confirmed, it is extraordinary. Right, so time travel forward in time is real. The question every Australian student asks next is, how fast do you actually need to go to notice it? Let us run the numbers. International Space Station, the ISS, orbits at about 28,000 kilometers per hour. Astronauts aboard experience time dilation from both their velocity and the slightly weaker gravity at altitude. The net effect? Astronauts on the ISS age about 0.007 seconds less per year than people on the ground. After a 6-month mission, an astronaut returns having aged about 0.004 seconds less than their twin on Earth. A tiny but real and measurable journey forward in time. Scott Kelly, NASA astronaut who spent nearly a year on the ISS, returned 0.008 seconds younger than he would have been on the ground. His twin brother Mark Kelly, who stayed on Earth, is literally 0.08 seconds older. To travel 1 year into the future in just 1 day of ship time, you would need to travel at about 99.99% of the speed of light. To travel 1,000 years into the future in a single year of ship time, you need to reach about 99.999999% of the speed of light. The catch, as we discussed in our interstellar travel video, is the energy required. Accelerating any object with mass to near the speed of light requires exponentially increasing energy. The closer you get to light speed, the more energy is needed. Reaching exactly light speed requires infinite energy, so forward time travel is physically real. The engineering challenge, building a spacecraft fast enough, is the barrier, not the physics. The universe allows it. Our current technology does not yet achieve it at meaningful scales, but give physics another century, and who knows? Now, the question everyone really wants answered. Can you travel backward in time? Feynman would insist on honesty here. So let us be honest. Physics does not definitively rule out backward time travel, but it does make it extraordinarily problematic. Special relativity says that traveling faster than light would be equivalent to traveling backward in time, information arriving before it was sent, causes following their effects, grandfathers being visited before they were born, the grandfather paradox, the bootstrap paradox, the cascade of logical contradictions that backward time travel seems to produce. General relativity, in certain exotic solutions, permits what are called closed time-like curves, paths through space-time that loop back on themselves, where following the path in one direction eventually brings you back to your starting point in space and time. Kurt Gödel, the great mathematician, found a solution to Einstein's field equations, describing a rotating universe in which closed time-like curves exist everywhere. Roy Kerr found that rotating black holes, Kerr black holes, theoretically contain closed time-like curves near their singularities. Wormholes, if they exist at macroscopic scales, which is deeply uncertain, could in principle connect different regions of space-time, including different times. But here is Hawking's famous response, the chronology protection conjecture. Hawking proposed that the laws of physics conspire to prevent backward time travel, that quantum effects near any closed time-like curve produce energy densities that destroy the curve before it can be used. The universe, Hawking suggested, is self-protecting against time paradoxes. This conjecture has not been proven, but it has not been disproven either. The honest physics verdict on backward time travel possible in certain exotic mathematical solutions of general relativity, likely prevented by quantum effects, certainly not achieved or demonstrated by any known process or experiment. Forward time travel, confirmed. Backward time travel, genuinely unknown. And that honest uncertainty is more interesting than any confident answer. Feynman had a deeply personal relationship with the concept of time, not just as a physicist, but as a human being. In his path integral formulation of quantum mechanics, Feynman showed that particles do not take a single path through space-time. They take all possible paths simultaneously, including paths that move backward in time. In Feynman diagrams, the mathematical pictures used to calculate particle interactions, antiparticles are described as particles moving backward through time, an electron moving forward in time, and a positron, its antimatter counterpart, moving backward in time, are mathematically identical in Feynman's framework. This is not just a mathematical trick, it is a genuine insight into the structure of quantum field theory. Time, at the quantum level, is not as strictly one-directional as our macroscopic experience suggests. But then, why do we always experience time moving forward? This is called the arrow of time problem, and it connects back to entropy, the second law of thermodynamics that we covered in our energy and aging video. The fundamental laws of physics at the microscopic level are almost entirely time-symmetric. Run a video of two billiard balls colliding backward, and it looks perfectly physical. Nothing violates any fundamental law. But run a video of a broken egg reassembling itself backward, and it looks absurd, impossible. The arrow of time. The reason we remember the past and not the future. The reason time feels like it flows in one direction. Emerges from entropy. From the overwhelming statistical preference of the universe for increasing disorder. Time's arrow is statistical, not fundamental. And that means, at some deep level, the distinction between past and future is less absolute than our experience suggests. Feynman knew this. He lived with it. He found it not frightening, but liberating. The universe is stranger than our daily experience of it. And physics, honest physics, keeps revealing just how strange. So let us bring it all together. Feynman style. Time travel forward in time is not science fiction. It is confirmed physics. Special relativity, moving faster, slows your clock relative to stationary observers. The faster you move, the more time you travel into the future relative to those left behind. General relativity, stronger gravity slows your clock. Weaker gravity, higher altitude, means your clock runs faster. GPS satellites above Australia prove both effects every single day, correcting for 38 microseconds of relativistic time drift, keeping your navigation accurate to meters. Muons from cosmic rays survive their journey to Earth's surface only because time dilation extends their lifespan. Confirmed, measured, real. The Haffel-Keating experiment, flying atomic clocks around the world, confirmed Einstein's predictions to within experimental error in 1971. Forward time travel is physically real. The barrier is engineering, not physics. Backward time travel, permitted in exotic mathematical solutions of general relativity, likely prevented by quantum chronology protection, not demonstrated experimentally. Genuinely open question, and at the quantum level, Feynman's path integrals suggest particles explore all possible paths, including backward in time. The arrow of time itself emerges from entropy, not from fundamental physics. Crikey. Time is stranger than any of us were taught. If this video made time feel genuinely different to you, smash that subscribe button and join the Curious Physics AU family. New videos every week built for Australian students and curious minds. Drop a comment below. What surprised you most? GPS satellites proving time dilation, the muons from cosmic rays, Feynman's particles moving backward in time. Tell me what blew your mind. Share this with every student you know studying HSC or VCE physics. Time dilation is in your syllabus, but not like this, not with the genuine depth it deserves. And share it with anyone who thinks time travel is just science fiction. It is not. Crikey. The science proved it decades ago. I will catch you in the next one.